In this video, we're going to talk about how to create a more sophisticated Basilisk simulation. So far, we've actually created a simulation that was pretty flat in its architecture, in the code. We imported all the modules, we configured processes, tasks, Basilisk modules, connected them, configured them, initialized them. Then we say initialize simulation, run the simulation, and then we log everything in one big Python method. Here, we're going to go into a different way of doing it. And we can go into integrated examples and this thing called bskSim. There's a whole series of examples here, and they essentially mimic what earlier examples do, but we're doing the same thing in a more elegant way. And I'll discuss exactly what that means, because there's always benefits and drawbacks to anything that we do. This video does assume you are familiar with Basilisk, and in particular that you've gone through the basic scenarios like scenario basic orbits, how to set up multiple gravity bodies, spice interface, how to do attitude control, set up those interfaces. So assuming you've already gone through these that have this kind of a flat simulation architecture where everything's in one big method. What we're going to do today is we're going to go through bskSim, and the first one is kind of like scenario basic orbit. So if you look at this script, there will be several support scripts. And the essence of it is that we will have a master class that controls which dynamics we're using, which flight software we're using. And it also another class that specifies how to initialize, how to configure what we're going to log, and how to pull data and how to plot it. All that gets kind of abstracted out. And so here you see two blocks. One is called BSK Dynamics, one's called BSK FSW, flight software. In this basic orbit simulation, we're just going to have a spacecraft in orbit around the Earth. And we are going to use SPICE. You're going to see that. So position will be relative to SPICE, but the functionality mimics scenario basic orbit with a little bit of the multi-body stuff built in. Flight software wise, we're not going to talk about this in this video. That'll be the following follow-up video. And so here it's just going to be in standby mode, which means flight software is not doing anything. It's not running anything. It's not doing any pointing. There's no guidance. There's no feedback controls running. It's just in standby for now. So this is just a spacecraft doing its natural dynamics. This will give some focus and scope for this particular scenario. Now, why do we do these classes? Everything's going to be moved into classes. And that's nice because if I have this flight software and this is a CubeSat, and I want to run one CubeSat, great. If I want to run a different CubeSat with the same functionality, it also has 4 wheels, it has these core sun sensors, but maybe they're configured in a different place, in a different way. Maybe the wheels are bigger, maybe they're smaller, maybe the sensors are located in other places. With the classic approach that you've seen earlier, you would have to go in and change a bunch of code to run that. What you can do here is the dynamics of a spacecraft has become encapsulated into a class. So when you're running the simulation in Basilisk, you basically say, look, I want to use these dynamics and I want to use these flight software algorithms, and I'm going to put them into these processes and tasks. You'll see this in a moment. And then run. If you want to use a different spacecraft, great, you can do that. You just import a different spacecraft model. And with just one line, you can actually change. Now I'm running this other CubeSat with the same flight software. And let's see how that responds. And that would work. So this is very powerful in how you can script, program, and run different simulations like this. But also I want to say this is one version you can do. You can, as we talk through the scenario, we will talk about, this is where we put this into a subroutine. That was a choice. You may make different choices. That's up to you. I just want to illustrate how you can actually make this more elegant than the one big flat architecture that we've had when everything's in one single Python method that we've had so far. Same thing with flight software. You can use the same dynamics and then switch out flight softwares, different algorithms, different things, different setups. What you can't do is if this flight software assumes you have 4 wheels, it's talking to 4 wheels, or it assumes you have a sun in your simulation because I'm processing sun sensors and doing safe mode. And all of a sudden you give it a dynamic simulation, it doesn't have a sun, or it doesn't have reaction wheels. this is not going to work, right? Because it'll assume some behavior on the other side of the wall. But you do have a wall all of a sudden between flight software and dynamics, and we can mix and match as long as it's done in a compatible way. You can't come up with attitude control that runs reaction wheels and there's no reaction wheels in your dynamics. That's just going to create heartache and crashes. So the text here kind of discusses what I'm going to go through, at least on a high level. So you always have this to look over and understand a little bit what's going on here. But what we're going to do now is actually talk through the code and what does this look like. First question, where is this code residing? It's under examples. If you look in examples, we've been talking a lot about these scripts that are just scenario basic orbit, like this one, or the attitude feedback one, which is up here. You know, we've discussed these already and gone through that. There is this subfolder called bskSim, and within it, there's some folders and there's a master file. This master file I've already got open up here, so that's the one that you see on the right-hand side. The models, this is where you can have different spacecraft dynamics, different spacecraft flight software classes defined. And we currently have only two. So there's the dynamics and flight software that we'll be using for most of the bskSims. There is a formation flying dynamics and flight software where instead of having one spacecraft, there's multiple ones, which works as well. But again, in this one, it's more of a legacy at this point because we have more elegant ways to do multi-spacecraft. If you want to see multi-spacecraft stuff, I would recommend looking at this folder, Multisat bskSim. It does it in a much more elegant way. Here, the dynamics is specified to be a certain number of spacecraft. So you only have two. Everything's configured for two. Flight software, everything's configured for only for two. Whereas down here now, we've been able to abstract these things out where your environment can be separate, your dynamics of a spacecraft could be separate. You can have multiple spacecraft. You just specify, this is a spacecraft times 100, and you have a fleet of 100 spacecraft. Very cool. They can also be heterogeneous. So if you're looking at multisats, I'm just going to highlight, go down here. The goal for this video is to explain this bskSim, which is the simplest form that we've had. Just what's the purpose? How can you architect? How can you package simulations, you know, in elegant ways? So let's look at this. We're going to jump right to the scenario. This is the actual simulation scenario. The master file and the flight software and this dynamics are kind of support. They specify the environment, the simulation architecture, and run it. And then the scenarios are here, and every one of them basically imports the master flight software dynamics. But then you're saying, hey, here I am doing attitude pointing. Here I'm not doing attitude pointing. Here I want to do hill frame pointing. So those are the simulation scripts, like what we had down here. But if you look at, for example, where's basic orbit? Scenario basic orbit. If I open up this one, there's a lot of setup. But you can see the main script sets up processes, tasks, sets up the spacecraft, sets up all the gravity bodies, initializes things, sets up recorders, you know, and then it has to initialize, run, pull everything, plot it, and do that. I'm going to close that one again. With bskSim, the actual running of it is really contained in this code. It's super simple. So essentially what you will see is this is scenario basic orbit. That's the simulation class. So we've turned the simulation script instead of a method, it's a class. This has some benefits if you have to run multiple instances of this. So that's a class. And we'll talk about bskSim and bskScenarios. They come out of the master. So I'll return to that. But this simulation class now, I create an instance of it. Then I run it. And in running, we have to initialize it. I'm setting a mode request. We'll talk about that a little bit more. For here, it's just standby. It's a new variable we're putting in there. We configure a stop time and we execute it. And that's it. And now we've run the entire simulation. So somewhere, obviously, we must specify how to initialize and things, you know. And then I pull the outputs. That means it grabs the recorders, pulls the data, and actually if show plots is on, it will plot everything and show you the results. As always in these scripts, we're returning a dictionary list of all the plots. That's just done for documentation purposes. You don't have to do this, but in these baked in scripts, we do. So when I run my automatic documentation creation, it can pull those figures and include them into the HTML documentation. So that's why we actually have this figure list returned. Not required, but for regular scripts. So anyway, so there seems some magic is going on here. That long file we saw, everything is done with these few commands. So how is this wizardry created? So let's go first into the master file. That was the one that is down here in bskSim folder. And you can see it's including simulation base class that we always do. And in fact, bskSim is defined to be a subclass of simulation base class. That means the bskSim class contains everything that the Basilisk architecture, making a process, making a task, executing, running updates. It can do all of that and some more. We're adding our simulation stuff on top of the basic architecture. So there's some things to define. In here, we see so bskSim, subclass of the simulation base class. There's a dynamics rate, there's a flight software rate. This simulation will use a single process for the dynamics with a single task running at some rate. And the flight software will also be one process containing one task, and it runs at some rate. If you wanted multiple tasks, you could easily do that. It just makes the script a little bit more complex, that's all. So we're keeping it simple here for illustration purposes. And you can see in the initialization of this bskSim task, the flight software rate, you can specify actually, and the dynamics rates you can specify, but by default, they would update every 0.1 seconds. So there was a mosquito. Okay, so that's what happens there. We create an instance, we also run init on the parent class, which you have to, and now we're creating some variables. These are kind of placeholders for now. So bskSim will have one handle called dynamics model. It contains this class that will know everything about the dynamics of the system. So including what spacecraft, what sensor models we're going to be doing, what effectors like reaction wheels and thrusters are added, the gravity, bodies, Earth, Sun, all of that will be included. Flight software, this is where we'll be specifying the flight software algorithms, the attitude guidance, the hill pointing, the attitude tracking error, MRP feedback, all those different modules we've seen before will be baked into that one. There's a single process for dynamics, a single process for flight software, so you can give them names. Here, they just initialize to none because they'll be labeled later on. And then the actual dynamics process will be stored in these variables. So these are all just initialized. So in Python, when you create a class, all the class variables have to be initialized somewhere, not just set. There's some faults. We'll be talking about that, but that's pretty slick. This example actually illustrates how you're not just baking in dynamics behaviors like reaction wheels, but we can actually bake in faults. This is a wheel, but every time I'm running update, there's a 0.1% chance the friction is going to go crazy and there's some stickage that happens. We can actually simulate faults and bake it into the dynamics, which is kind of slick. So I'll talk about that. Here we're just initializing it. So I'll return to that when we actually talk about the things. And these are two other flags that check if you want to see, has the user actually added dynamics? Because if they don't add dynamics, this master class is just going to go, I don't know what you're talking about, So we're setting them to false. So at front, nothing has been added. Now, there's only a few methods in this bskSim class. So it initializes, creates these placeholders for the processes. And then we have one that says set dynamics. So this is where the user provides this Python file, essentially, that was imported. And within it, and then if this gets called, the dynamics is flagged as being added. The process name is being specified here. And then we create the process for the dynamics. And that's put into dyne process. That's what we saw earlier being initialized to none. So now it's no longer none. And we actually need the dynamics modules. This is the class that contains spacecraft, Earth, Sun, external force torque effectors, thrusters, reaction wheels, all those modules. So this one was provided in. You will see this in the next file. Then this was provided in during the setup. So we tell it which spacecraft dynamics to model to do, but the name of that one can be called BSK dynamic models. And we specify the rate as well, which was defaulted here to every 0.1 seconds. and unless overridden in the constructor, which you could do as well. So you can see this sets the dynamics model. Get dynamics model, you'll see this in places. If we have access to this bskSim class, we can always do .dyne process .something within it. Or if you just want to return that, you can also call get dynamics model. And if it has been added, so it does it in a little bit safer way than just directly reaching in and grabbing the variables, it'll return the dynamics model that was imported in this process right here. Flight software is really analogous, and here we're not running any flight software. Everything's just going to stay in standby mode, so I'm not going to talk much about these. So that's it, bskSim. What are the key takeaways? It's a subclass of simulation-based class. So if I make an instance of bskSim, I can still do initialize simulation, execute simulation. All of that still works, but I've baked on top of it these processes and some fault flags for the system. There's another class, bskScenario. Again, it was chosen to do this separately in 2 different classes. Don't have to do that. But this sets up stuff that we need. Every simulation needs to configure initial conditions, because I could run this scenario basic orbit, but what if you don't want to run an elliptic orbit? You want to run a hyperbolic orbit. You want to run a polar orbit. We should be able to write a script that uses everything from before, but just changes different initial conditions. So somewhere we specify those, and these are just dummy functions created for the class that do nothing. So the user is expected to write proper functions that does something. Log outputs, you're telling it which variables to log, and then pull outputs, you pull those recorders and plot. That's what we've seen. When we saw this one run, it called pull outputs after doing everything there. Okay, so that's the master class. That's kind of bskSim, sub of simulation-based class, dynamics. It has the processes defined. And this other one defines configuring, what to log, and what to do with the log data, those 3 things. Great. Now, let's go into the actual scenario and look at how this is configured. So here, from bskMasters, that was this file here, we're importing bskSim and bskScenario. Those are the 2 classes I just talked about. And bskSim was a subclass of simulation-based class. We're also importing bskDynamics, that's this one up here, and bskFlightSoftware, that's this one. And again, I'm not going to deal much with flight software right now, so we can ignore that. Plotting, that was actually put all into a plotting one. If you go look here, there's a plotting routine, so it just abstracted out. You can go look at that on your own time. That's pretty straightforward, Basilisk stuff. So now the simulation, we said, has been turned, instead of just a method within a Python file, we're turning the simulation into a class. And in fact, this simulation is a subclass of bskSim, which is also a subclass of simulation-based class. So scenario basic orbit will contain everything from simulation-based class. You can initialize and execute simulations, create processes, do all that. But it also has all the abilities of bskSim, which added these 2 specific processes that we can set and get and assign dynamics in flight software. It's also a subclass of bskScenario. So an instance of this class can configure the simulation, set what to log, and pull the logs and plot. So that's initialization. We initialize the class. We give the class a name. Then we have some recorders here. There's only 2 recorders that I have to initialize a priori, so I set those there. We had the set dynamics that we talked about. That was here in the master class. This is where we specified to the master class, I want to use these CubeSat dynamics, not the other ones. So here we're specifying bskDynamics from what we imported. So we'll look at that file. This file is already open. We'll talk about this. This will be a longer discussion in detail how everything gets set up. So this is where we set the dynamics, and we also imported flight software, even though it isn't doing anything here. We imported flight software, and it gets set. Then we call this command configure initial conditions. So we need to actually define that somewhere, and you will see that down below. So we call that, but being part of bskScenario, this is one that's expected to be defined. And then we also call log outputs, which we'll talk about down here. So that's the one that sets up what to record. The rest of it, this is just for running enable visualization, Unity visualization. where we have to give it the task name, the spacecraft object, and so forth. So this is an example where you can see before we just had SC object defined within the run method, and everything was flat within inside that one Python method. Now that spacecraft object actually resides within the dynamics models, which here you can see is an instance of BSK dynamics modules, and that's what was provided. So from that Python script, the dynamics class is called BSK dynamics models. So just jumping around, that's why you can see here, this is a copy of, that's the instance of that, stored within this main class. So adding things like effectors or spacecraft or other things are done. You just have to go into the master class .dynamics model then that's where everything resides, including the task name. And we will see all these when we talk about that class a little bit more. Anyway, so this is an example. So I configure, I've initialized now my simulation. I've already initialized, I've set up also log. So what goes into the configure initial positions? Here, we will need to set the spacecraft hub position, initial velocity, initial attitude, attitude rates, all of that like we do in other simulations. But the spacecraft object would be created within this class here. And again, we're going to go through that. So the get dynamics object that was defined in the master class here, right? It simply returns self.dyn_models. So in this code, instead of having dyn models here, I could have also written actually slightly longer self.that. That would have worked too. It just gets tedious after a while. So there was a choice. So using the get models, I can get a shorter variable that I can call, and then within it, the spacecraft objects are there. And then I initialize the positions like we did before. This code is just using orbit elements like we've seen in the earlier simulation scripts and scenario basic orbit to set up which specific orbit we are simulating. So if you wanted to simulate a different orbit, instead of this one that has an inclination of 30 degrees, you want to do a polar orbit with 90 degrees, you'd make a copy of the script. This is the one line you'd have to change. Nothing else would have to change. And you'd be using the same dynamics, the same flight software, and it would just run it now in a different orbit. And you can see this gives you nice scripts that can run the same dynamics, the same flight software in lots of different configurations. And you don't have to keep editing the same script over, and that's more error prone. So we've configured the initial conditions. The next one up here was log the outputs. And so basically this is where you set up your loggers. And again, I'm using the get dynamics model as a convenience. So I can just get this handle, and then I can say dynamics model dot whatever these modules are. In the earlier code, we had the simple nav object that we created, the Basilisk module dot output message dot recorder. So now it's going to be dyn models, right? Everything dynamics is embedded into this dyn models class. And so that's the only difference. So we set up the recorders, and we also add them to a task. And the task will be specified in the dynamics module. So it's in dyn modules task name, and we add that recorder that we created. So we only have 2 recorders. This is why here initialization, we just did those recorders were initialized to none. So Python had all the variables initialized up front, and then here they actually get set. When you go look at the simulation itself, we create an instance of this simulation that does all the initialization. So all this stuff up here happens. So as soon as you create an instance, we have set dynamics, we have set this, we have configured initial conditions, and we've configured our recorders. So this one line does all that magic, and it returns your instance of that class. Then we're going to run scenario. So here you can see the run scenario is a method in this file. You could have taken all this code and just put them directly down here. That's fine too. So here the choice, in the script, the choice was made to spit that out into a separate method. And that calls initialize simulation. This is what we always do in simulation-based class to set up Basilisk. This is going to run, you know, the self-init and resets on all the Basilisk modules and get everything ready to run. Mode request, this is a variable we're specifying here actually, and we're just saying it to be standby. Flight software will care about that. This particular simulation doesn't. But we set it just because we do include flight software, making a complete spacecraft here. We're just not turning on flight software. Then we set the simulation time, 10 minutes, and when to stop, and then we execute it. So all of that is inside the run. And then the last one is pull outputs, right? And that's called off this scenario basic orbit class. So if you look at that last one, that's where you basically take your recorder. Here we're pulling out the attitudes, the position, the velocities into separate variables. And then we're calling a bunch of plotting routines to plot it and show you what it looks like. So if I would go to that folder inside examples slash, let me just print. You can see here, this is under Basilisk examples, bskSim scenarios. If I run this one, it'll execute the simulation, and I'm plotting some orientation states, some orbit radius states, and you know, it does just this typical plotting that you would expect. And that's it. So this is all the magic. We got the parent class that needs to know which dynamics, which flight software. We've got the simulations that are now wicked simple. We specify what these things are, we initialize, we set up what to log, we quickly configure that, and then the simulation run is super simple. So if you want to have 16 different versions of the same spacecraft in this running, you can just import these things as classes and run them without ever having to touch the base spacecraft. Or vice versa, if you got 16 analysis scripts and all of a sudden the mass of the spacecraft changes from 50 kilograms to 80 kilograms, you don't want to go into 16 scripts and change that. That's error prone. Here, you change it in one place, rerun the 16 scripts, and they're all going to import the proper dynamics and give you the analysis. A little dry throat. Okay, too much talking. Now, what we haven't talked about is all this black magic of creating a dynamics class, right? So here we import this file, and within that file, like when we set it up, we just pass on that file. That's what we imported in set dynamics. And in set dynamics, that's what we imported. We assume there is a class called BSK dynamic models. That's what we're going to look at next. This is where all the encapsulation, all the packaging happens to create this spacecraft dynamics class. Okay, so this is BSK dynamics. Here we have to import everything that's dynamics related. So the spacecraft, external force torque, simple nav, reaction wheels, coarse sun sensor, there's an eclipse model, there's a thruster, there's an ephemeris converter. The ephemeris converter converts the planet spice message, you know, the ephemeris, where is Earth, what's its orientation, into a flight software planet ephemeris message. So that's what it does. There's these thruster factories, reaction wheel factories, gravity body factories, and some other support libraries. So all the classic dynamic stuff gets imported. And now we're defining this BSK dynamic models. That's what we're creating an instance of that here in the master file. So this is now going to have to do several things. It's going to create all the Basilisk modules associated with the dynamics. And in this case, also the environments, like Earth and Moon and all embedded here for what we're orbiting about. It's also going to have to create tasks and then assign these modules to tasks. That happens all in this class. So in this simulation, we're doing a single task. If you have multi-tasks, you'd have to create multiple tasks and then make sure your codes are compatible. And it has to also configure these modules. What mass are we using? Where is this reaction wheel? Where is that thruster? You know, and it has to connect all the messages. So it has to do all of these different tasks. So that's embedded into a class. And you will see this is not the only way you could write this. It is a way that we're going to illustrate, but you could make these classes look differently if you had a need for that. There's a variety of class variables that all get initialized to none. This is just because Python classes should have all class variables somewhere initialized and on defaults. So that's done. What these are, we'll talk about a little bit later. So here in the initialization, we also create the process name, and because we need to know that. And sim base, you notice that's one that we provide. So that's big backwards. What is that sim base? When we create that, this is self dot. Sorry, that's the self. We're passing ourselves. This is the master class. And the master class was also a subclass of simulation base class. So here we go. In here, SimBase, think of it essentially like the simulation base class that we created in the earlier flat scripts. We can now do things like create tasks from there. SimBase, also I can pull the process name because I need to know to which process do I add my task. So that's what's coming from here, and I'm storing off the process name. The task name I'm specifying as a class variable as dynamics task. I'm specifying the update rate of this task, and that's the dyne rate. That was also provided by here, by this initialization. So that was defaulted to 0.1 seconds, or 0.1 seconds. So this is all being initialized. Then I have to create a single task. So that's happening in this line. So like before, we're creating a task with a certain task name and a task update time step. And that task gets added to the process, but that process is part of simbase.dyne process. So we've now added this task to the dynamics process of the master class. The next step, we need to create all the Basilisk modules that the dynamics requires. So we have here the spacecraft. We're creating the graph factory copy because we're going to be using this to creating Earth and Moon. We're going to create a reaction wheel factory. We've created the external force torque one, the simple nav sensor module. We're creating an eclipse module, coarse sun sensors. We're creating reaction wheel effectors, thruster effectors, and this ephemeris converter that flight software needs because it needs a flight software planet state message, not a spice state message. So that's cool. So now we just created objects, Basilisk modules, but they're not initialized. They're not configured. We haven't specified what the spacecraft mass is, or we haven't connected any messages yet. We've just stamped out prototypical modules. The next step is initialize all these modules. And we'll jump into that routine in a second. It's pretty straightforward, but I'm going to go through that in detail. So this would actually specify what is the mass, where is this wheel, you know, and all of that. And then we have to actually add these modules to the task. And we only have a single task here. So every one of them gets added. And you can see here too, they're added with priority. So those with higher priority, like here, these effectors, they get run first. We want to read in the torque command before we run our dynamics, you know, and then the spacecraft, and then this one, and then these others. So you've seen before how to do priorities. So after all of these lines, we now have at least all the dynamics Basilisk modules added to the task. So when we call update, it will update all of these things properly. The next thing, the last two things that we're doing here actually is pretty cool. This is a more recent thing we've added. We're illustrating here how in the dynamics, we're not just saying, look, there's a reaction wheel, but we can actually create, we're using the simulation base class event handler, where we can specify a condition under which something changes in the dynamics. So for example, reaction wheels, if it starts breaking down, the bearings break down, the frictions increase drastically all of a sudden. So we're going to look at a one-time event that we can set, or a repeated event. Maybe it just sticks every once in a while, and there's a 0.1% chance every update cycle that it would stick a little bit more. That's something we could simulate. So how does this event handler work? You give the event a name, that's the first string. Then you have to give it the process task time step, which we do. Then true, that means we're setting an event that should be active. And now the interesting part is we give it two lists, and these are lists of strings of Python commands. It will then loop through these strings and evaluate these Python commands. So the first condition is really just, is this condition true? If true, then this event is triggered. And so here we're saying under self, which is the simulation base work, total sim, current nanos. This is how we pull the current simulation time. If it's greater than this one-time fault time, that's a variable we set actually in this class. And this flag is set to 1, meaning it's true, it's not off. If those both conditions are true, then it's going to have another list of two different commands to call. So it's going to have this add fault command, which adds some friction faults to the system. And it also turns off this one-time flag, this one-time reactional flag. So if it was on, it would give a fault once, increase that friction, and then not trigger that fault again. So that's how we do a one-time fault. And these other flags, these were all things that were initialized. Where were they? Here we go. They were in the master class. They were initialized here to the fault flags are off and the fault time is -1. That's not possible with Basilisk simulations because it's an on-site integer. It's always going to be on. So that other one is always going to be true. So just basically with if you just ran the simulation as is, it would never trigger this fault because the fault flag is always off. This fault time is set up. You may want to say, look, let the simulation run for at least 60 minutes. After 60 minutes, then I want to fault the wheel, you know, and only one time. And then that's what you could specify. So that's just an illustration how to do it. And we'll look at the add reaction wheel fault here in a second. The repeated fault, there's a subtleties there because if you add this event doesn't actually necessarily get turned on again. Anyway, so here we have an event where we create a repeated fault. We want there to always be a probability. And so there's a periodic reaction wheel fault command that we want to call. And the condition is just if the repeated reaction wheel fault flag is on, it's set equal to 1. So if you made that in a master class here, 1, it would run it with these errors. Then it's going to run this periodic fault, which actually checks. There's a 1 in 3,000 chance essentially that this fault would be triggered. We have to give it the simulation time, and if yes, the other thing it does is set event activity. So this event, if it runs, it goes to off. So you don't just repeatedly run the same event over and over again. But every time we run it, we want to make sure we reset that flag or that variable to be back to on again, to true. So that's what that second command. Without this command, you wouldn't get repeated triggerings of these things. If we go look at add reaction wheel fault quickly, this would be very fast. So here's the command. We basically check, we do a little bit of reaction wheel log logging. It's just nice for post-processing to see, did we trigger a fault in the sim and when and what, just so you have a record of that. Then it looks for the type of friction. If it's a friction fault, that's the only one implemented right now, right? It also checks which wheel to fault, wheel number 1, 2, 3, or 4. It reaches inside and it will change the Coulomb friction coefficient by adding this fault value to it. So every time it's triggered, it's going to bump up that friction coefficient. If we have this periodic reaction wheel fault, it checks this uniform random number to be less than this 1 in 3,000. And if yes, then it runs this fault. So you can see there are just two different methods on how to call that. Anyway, now this is a lot of discussion on initializing. But we're not quite finished yet. There's this init all dynamics object. So let's dig into that quickly. What does that method do? So that calls a bunch of other methods. So again, that was a choice to make this one method to call an init, but then you have embedded here where this all gets called. And we will set up the spacecraft, we will set up the gravity bodies, we'll set up the external force torque, and you will see what the setup actually entails, because it's not just setting the variables, we also have to do connections to messages, connect the message input outputs, and so forth. And in some of these modules, it doesn't matter when you initialize them. Other ones, it will. So for example, set the eclipse object has to subscribe to the sun, but the sun position isn't set until after I have initialized all the grav bodies. So for a few of these, it is important that you do one first initialization, then the other. So just be aware of that. But let's go look through these quickly. So this initialize all objects, we've already created the Basilisk object. It's stored in SC object within this class as a class variable. So now all we do, like before in scenario basic orbit, we're going to set the model tag. I'm setting the spacecraft inertia. I am setting the mass and everything else that I do with the spacecraft, basically. So very straightforward. I'm just creating all this. There's no other messages to connect here. The next one, set gravity bodies. This is where we're setting a time string, because we're using SPICE actually to specify. We're going to have Earth, Sun, and the Moon. So this is actually a little bit more complicated than scenario basic orbit. We just had create Earth. But I need a Sun for my core Sun sensors and the Moon just for kicks and grins. You know, we can add it. So we can do that. We use the graph factory here, and we already had an instance of that declared in the initialization of this class. And then this returns that dictionary list. So within that dictionary list, the Earth is set as the central body, and you've seen that what that means. These flags, Sun, Earth, and Moon, when we use SPICE, it creates a vector of output messages. And since we specified Sun, Earth, the Moon, this is an ordered dictionary list. The module will have a vector of output message, and the slots are dictated by this order. So these Sun, Earth, Moons are really just integer slot indices that tell me the Sun will be at the 0th position of that output vector, Earth will be at the 1st, and the Moon will be at the 2nd slot. That's all. So the benefit is because later on you'll see in the code we have to add some stuff and connect to the right message. And if I ever made the Moon the first object or the second object, I just have to change these indices and the rest of the code should run, as you'll see. Let's see, what's the rest? You can see for the spacecraft, this knows this is its own class, so its SC object is a class variable. Every other method in the class can access it. I can just add the gravity field to the with grav bodies like we do in all the other scenario basic orbits. This is where we adding grav bodies as an effector to the spacecraft. Then I run my SPICE interface. I just have to do it on the graph factory instance of this class. So we talked about that. I'm actually saving off the epoch message into a separate standalone message within this class, just out of convenience. I am setting Earth as the 0 base. So any logging is done relative to the Earth. So from spacecraft motion, not relative to the Sun, which would be the inertial frame of SPICE. And here, this ephemeris converter, we said there's a module that takes a SPICE planet ephemeris message and converts it into a flight software planet ephemeris message. And that's the ephemeris, Earth ephemeris object that was initialized here. So you can look up ephemeris converter if you want to read more about that. So in that one, there's a method called add SPICE input message, because it doesn't just do it for one, it can handle a number, a vector of these, and you have to add them with this add function. But I have to specify which message to convert. So the SPICE object resides in the graph factory, and we specify the planet's out messages here. It's a vector, so I have to give it the right index, which would be 1. But instead of hard coding 1, I specified here that that's going to be 1, just for convenience. Anyway, so all of that sets up the graph bodies and the conversions of the graph body states. Again, it's a choice how you want to order these. You could have made this one big routine that initializes everything. Here it was done individually. Set the eclipse. Similarly, we set the model tag. If you look up the Eclipse model, you have to subscribe to the Sun's message. The Eclipse module needs to know where is the Sun. And so I'm subscribing here. SPICE object is the vector of output message, and I need the Sun's slot, which is the 0 slot. Then I am looping through a bunch of other effectors because it does eclipse not just for, it has to know about, am I being eclipsed? Am I flying through the shadow of the Earth or the Moon? Because it will do either and tell it. So here I have to add we have Earth and the Moon. So I'm just looping over all these output messages, and I'm excluding the 0th one. That's why I'm starting from 1, because the Sun is the 0th. I need the planets. So I purposely chose here to have the Sun as the first slot. And then I add this SPICE eclipse command, add planets to module. This stacks up these vectors, and it will start reading in all these input messages and convert, and then it creates a vector of output messages. And then I have spacecraft object, add spacecraft to module. So I have to add the spacecraft to this one. You can also have a vector of spacecraft that it loops over, and it creates a vector of output messages. Anyway, so you can see, you can read up on the Eclipse module, but this is where I'm configuring it. External force torque is pretty straightforward. I just have to create the model tag, and then we add that dynamic effector to the spacecraft, and that's it. And simple nav, same thing, we create that, but the simple nav needs to subscribe to the output of the spacecraft state message, which would be self.scobject.sc state out message. So that's done just like with some of these other flight software, reaction wheel, just scenario, attitude feedback.py is one that does a very basic version. Next, we need to configure reaction wheels. I'm assuming here you've already seen something like reaction wheel attitude feedback scripts, how to set up those. So I'm specifying the max momentum, how the wheels, where they're positioned, what are their orientations. That's what I'm computing here. And then I use the reaction wheel factory to create the wheels. I'm saving them off as RW1, 2, 3, and 4, so I can access them later easily. And the big reason for this is faults, right? We saw earlier, if we're setting a fault, I want to be able to reach into reaction wheel 2 and specifically change that F Coulomb variable and increase it by some number. That's why we're saving these off. Otherwise, that wouldn't be needed. Then set thrusters, very similarly. We've gone through the thrusters stuff earlier. We're setting up the thruster factory, creating the positions, orientation of the thrusters, looping through that to add those all to the thruster factory, and then we add them to the spacecraft. And so we provide all the same states. So it's just we're putting all the stuff that was in one big method before and stacking them into little methods that get called by the initialization. Core sun sensor, similarly, we're adding the model tag. We're going to loop through all the devices. We're running a setup command here, actually create that, and then I'm running that setup command to, there we go, to create all these core sun sensors. I'm making an object. I create the device. This configures it, and it also, you can see it does all the required. It needs to know where is the sun, where is the spacecraft, and then what is the eclipse. Am I in the eclipse right now of any of the planets? Because that will impact my message. So that's the core sun sensors. We've got those all configured. The periodic faults, those ones we've already done. And that's it. So now you've seen this basically takes everything that we'd used to do in one big routine, breaks it up into all these different smaller chunks. And the big benefit here is really the encapsulation. All the dynamics is now compressed into a class. And that makes it easy if I don't want to run this dynamics here, but I had another one called the dynamics special or something, not defined. I would do it, change this name here, and as long as it has a compatible configuration, but it can have different mass, different location of the wheels, all of this stuff, you can very easily do switches and not have to rewrite all your scenarios. You just pull in a different one. And that's super powerful. Okay, yeah, so hopefully this gives you a good overview of BSK Dynamics, in particular bskSim with BSK Dynamics. So that's where I'll stop here. The next one, we'll actually talk about the attitude feedback. So that's where we talk about flight software modes and get into a little bit more of these events, how we can use events to lots of tasks in flight software and turn them on and off, because if I'm in sun pointing, I might do different things than in hill pointing. So that's kind of the purpose. Anyway, hope you enjoyed. Hope you got something out of this.